So I just want to introduce our moderator for this session, which is Steve Hines, who is an educator and architect. And so I'll knock back the word in with us. Welcome, everyone. I'm so excited to have you all here. It's a wonderful afternoon ahead of us. But yes, my name is Hugh Hines. I teach here in the architecture program, CCA. Worn several hats, but most recently, the work that I've been doing here at CCA has been primarily geared towards the practices program, which has a relevance to our panel we'll get to in a moment. I'm also a co-founding principal at Proto here in San Francisco. We do work that kind of deals with architecture of mobility, architecture of production, and the super Spartan industry. Overall, just really interested in ways in which industrial techniques, industrial production can be mobilized for smaller scale applications, perhaps trying to counteract some of the mass production coupling with industry that's been, I would say, actually a major defining feature of some of our 20th century architectures. So should we shift into kind of opening the mark, or we definitely look at we was talking about absolutely. So it's extremely exciting for me to be moderating this panel. Just on a personal level, so I grew up in a family of biologists. Studied biology in college before switching to architecture. So to a significant degree, this kind of feels a little bit like coming home, which is wonderful. But I would also say that one of the remarkable things about our panelists today, and really their contribution to the biomaterials, really emerging subdiscipline, I would say it kind of really has a more extensive set of implications to a broader set of problems about how do we translate innovation in architectural design research, and perhaps design research more broadly. How do we transition that out of the studio and out of the lab and into the wider world? It's just been really wonderful to kind of learn more about our panelists, and it's really kind of come to see them not just as a set of innovators in their work, but also really thinking very critically about how that work gets disseminated and proliferated throughout some wider context. So we'll be talking about that wider context in many cases. But just to sort of pull back the frame of reference a little bit, as I mentioned, I think part of what makes this panel so notable, again, not just their contributions to biomaterials, but really what the implications are for us as educators and practitioners, thinking more broadly about how we transition research. And I would say that, as I was preparing for this, I kept being struck by what the parallels of the dilemmas that were being faced by our panelists in transitioning work out of the lab, out of the studios and biomaterials, and into some application, whether that's industrial core, the job site, or the factory, or even another planet. And many of the sort of the capabilities and challenges that our panelists encounter, I think, are actually mirrored in a lot of what we're tackling more immediately in school, kind of within our architecture education. And so directly, this impacts, I think, our practices curriculum. And one of the key questions or challenges that we've been studying over the course of several years in that curriculum has been exactly this problem. How do we take innovation and make it applicable? How do we transition into an outside environment? And it's perhaps going to be easier said than done, but the capabilities that are required in order to be able to do that effectively are critical. That you really, it's one thing to have innovation; it's a very different thing to actually disseminate that. So the capabilities that are involved in learning how to do this more effectively might be quite rudimentary. It might be things that are, tend to be rather boring, right? Things like contracts or insurance or liability, right? Nonetheless, these are critical capabilities that if we don't take them seriously, we don't learn how to manage them effectively, they can come back to bite us later on with impasses as we begin to sort of execute our work. And I guess the other aspect of this I thought was particularly notable in Jimmy's lecture last night was that if we call those kind of capabilities perhaps the sort of front brain kind of capabilities, or also these kind of rear brain capabilities, the sort of more improvisational set of tactics. So Jenny mentioned this, so that is the sort of behaving like magicians, right? Where when it comes time to actually put something into implementation, right before it's released, right before launch, there are inevitably problems, and how we contend with those problems, how we develop those muscles to respond to those is a really kind of critical part of what it takes to make something viable. So these are a lot of the considerations that we've been really trying to look at in practice this program. Certainly wasn't part of my architectural education, and I would say broadly historically has been a kind of a blind spot in architectural education overall. And that, as practitioners and researchers, when we encounter these things in our careers, we're often having to invent them on the fly, then sort of learn by doing. And, I would say that that's all well and good, but in many cases, we end up sort of having to play catch up and run the back foot a little bit. So with all this in mind, I do think that our panelists, while of course we're here to have a very focused discussion about biomaterials and some of the specific challenges facing the translation of biomaterials research out of the lab, out of the studio, and into some form of implementation. I do think that these panelists do have a lot to offer more generally to the architectural discipline. As Margaret Never just said, if you haven't seen the exhibition, time's running out, so get the on over there. But I would say that see you. I would say that it's quite clear that this is a really exciting point of transition for biomaterials as a subdiscipline in general. I would say that there's the evidence that was clear in the exhibition, but the research has developed what I would say is a critical mass. There's been a critical mass of research. And secondly, I think that research has demonstrated in time kind of incredible viability, right? That it's ready to launch, it's ready to go. And I think a lot of our panelists will be sharing with us today kind of a lot of the challenges, what it takes to actually get over that hump, right? From that credible viability comes with it a set of challenges, a set of mandates in a way to propel it. With the lab, it's not just that it can be implemented, it can have an application, but it kind of must have the application. So this is tremendously exciting. The work, as you can see in the exhibition, it's not hypothetical, it's not speculative, it's tangible. You can pick it up and hold it in your hand, or at least you can pick it up in your hand. There were all these do not touch signs. Probably not alone, but I don't think I've ever been so frustrated walking around a submission. Just great. But yeah, that's great. Little note for you there. So I would say that our panelists here are really sort of emblematic of this kind of almost poised sense. It's like a coiled spring. They're ready to go. So with that in mind, I would really sort of want to kind of focus our efforts this afternoon on how can we make this actionable, right? We don't want to just talk about this in casual terms, but really what are some of the concrete steps that we need to be taking together as a discipline, and even for those of us who might not be directly involved in biomaterials research, how can we kind of support those efforts through bolstering other aspects of the discipline, whether that's through architectural education and training a different set of capabilities that might serve well or to the young students and practitioners who might be headed towards the biomaterials kind of from some of professional goals. And similarly, how do we kind of work, what would this be? Intradisciplinarily, right? How do subsets within the larger architectural and design disciplines support each other and could really leverage what's been so exciting about biomaterials to propel innovation forward in a more broad sense. So with that, I want to welcome you all. Thank you so much for coming. We're supposed to invite our panelists to come up and join us. And how to
You guys, handle it.
so I can see under your photo. Yes, let me just take the photo.
Yeah. Shake it up. Yes. It should be. Oh,
So we have a screen. So maybe we can kind of go down the row, starting with you, Rick, and have you each introduce yourselves, and then maybe share kind of a couple of quick thoughts about your work. From the other side, I'm sorry. Honest, I apologize. You may start here with.
That's like,
Yeah.
it's other, maybe it's other. Yeah. Can you hear me?
Don.
No, does it go?
Hold it like this and then that's all. And
It's for my engineers. Farming cap. Actually, it might be battery because it's a red on my.
Lead the
Up and wait. Yeah, and then.
Wait.
Was okay. Yeah. Alright, so good afternoon. Yeah. I'm Anastasia Mulyana. I am actually from Mechanical Engineering Department at Texas A&M University. Just a bit of a background. So my training is actually in civil engineering, structural engineering. So I got interested in geometry and structure. That's what I go to civil engineering, right? So, but later on I learned that what I actually like, partial differential equation. So it's not really about concrete or steel. That's what I do, a lot of computational work, theoretical work. Then I go to grad study at Georgia Tech. Again, I told my advisor, I only want to do computational work, no experiment whatsoever. But of course, it doesn't work like that, right? Because then, like mentioned before, I have to show something that you can touch, and not just in a computer simulation. That's what my advisor made me to do experiment, making composites, and so on. That's how I learned, like my friend at Valeria helped me making composites, right? So that's why I go into this business, mechanics of composite. I learned about polymer. Then I graduated, I moved to Texas A&M. Then I got interested with we call like a flexible reconfigurable structure because one of like defense industry, aerospace application, that. Then down the road, of course, still within this differential equation, I learned about like long-term durability, physical elasticity, wave propagation, and so on, right? So most of the time has been really doing all this computational work. So until like we do experiment, but mostly collaborating with experimentalists just to get data, right? So now the question is like, how did I get in here? I forgot how, but for sometime somewhere at Texas A&M, I met Nega. So then we start working with undergraduate project, like she want to have a mold that is reconfigurable for concrete. So we had a project together, an undergraduate project, the undergrad work on that, multidisciplinary from different departments. Just to brag, our team won #1, right? Yeah. So that's why I started in this engagement. Then Negar took me to her lab, showing me curving. That's the first time I heard about curved structure. It's nice looking, like wood structure with a lot of cut in it. Then she said, okay, I want to do some stress analysis or calculation, so then we know how to cut it, right? I thought, okay, we can do that. But then again, I thought, okay, if I do this, yes, I do this, I have a student to do that, but what else, right? So you can do with that. So now I start thinking, if I want to do it in the long term, it has to be something in the engineering side that I got excited and my student would benefit. So now that's the first, like you look at curving. Now for the engineer, you look at that pattern, so those like the cut, right? So it's really good for wave propagation. Because the way you make a cut, then you make it either difficult or easy for the wave to travel. So what we can do that is actually for vibration suppression, or like could be acoustic damping or vibration damping and any other wave-related study. That's what we studied there the first time, right? So we look at all this wave propagation. So then, yeah, now I was thinking, now, like, what else we can do with curving? So we explored with printing, like multi-material mixing. Now we can say, okay, what about if we have a gripper, like robotic finger, right? So I'm thinking in the long run, we want to do this like for soft robotic, for agriculture, because at A&M we have big agriculture department. Now, while we said, okay, if we want to grip, we want something to be able to treat like delicate fruit, like tomato, strawberry, and so on. So now we don't use metallic finger, right? So then make it out of this curved structure because so many design parameters you can do, from the material, the geometry, and so on. Then we can also change the tip, so then make it like less, make it more friction, right? So then you can grip without slipping. So that's the idea of all this exploration. So now since this topic is related to biomaterials, right? The question is, what have I done in biomaterials? Again, the advantage of being at Texas A&M, we are big in agriculture. So the project we had to study sorghum stem, because our collaborator, they grow a lot of sorghum, is healthy, but they are all fracturing or collapsing because of the wind, right? So then the question is, why that happen? Of course, like in engineering practice, before we decide something, we do all this structural analysis. So we brought the mechanics aspect, the structural aspect to see how the sorghum fail. Now, of course, like based on my past interest, right, so I was just thinking, okay, yes, it failed, then what? They asked, okay, can we make it stronger, right? So of course you cannot like insert metal structure there. Then I was thinking, okay, this is a biological material, is adaptive. Can we make them exercise, like human being exercise getting stronger, right? So how to make plant exercise? So we create all these shakers with vibration control, then you can control different frequencies. So we shake them periodically, like during their lifetime, like 7 weeks, actually not that long. We time it like 1 hertz, or then you check the period. Then you saw a significant difference in their morphology and anatomy. The one that is being shaped or do exercise, they get thicker cell wall, but they are short. So now we test mechanically. So then it turned out to be a lot stronger, double than what the one that is not being exposed to exercise. But they are so flexible, they are bending. So that's maybe the idea here, okay, maybe they can sway better with wind without breaking. So now we really would like to continue the research, like from my end, like, okay, can we do some other mechanical stimulation? Because it's not practical, right? If you want to do it in a larger scale, you cannot expect until the earthquake comes. So then can we do acoustic, like a much smaller, but it's high frequency? That's what we are exploring. But my collaborator in crop science, they are more interested in gene expression. What is being expressed and those kind of things that I'm nothing or no idea about. But this is what they are actually really looking into. It's not my idea like, hey, we make them exercise. Now the last one, that's I work with a lattice structure, but this is biomaterial in the sense that it is biodegradable. We work with PLA, PLGA, polylactic glycolic acid. So the idea here is for like implant, like a stent. So again, I do all this simulation. I have a collaborator who's making the sample and doing the testing. What we want is to control degradation, right? So when you implant it, so you don't want it to stay too long, but you don't want it to degrade too fast. So now again, it's partial differential equation. You do all this kinetic. So then we see how long it degrades. So that is actually what we have done and why that I'm here. My claim to fame because I know Nega. That's all.
When you used to gross mine, there we are.
Oh, great. I can't see what's behind me, but I'll just assume that it's something else. So my name is Lynn Rothschild. I'm your local space bird. I've been at NASA Injury Research Center since I was a postdoc, sometime before many of you were born, probably. And my background is actually evolutionary biology, but unlike you, it's the reverse. I have a couple of artists in the family, but I was the one who ended up being a biologist. So my interest really has been in, as my dad used to say, little wiggly things that was within protozoa and algae, and so I, then picked up evolutionary biology along the way, using molecular techniques to look at evolution, and ended up at NASA to look for life in the universe, which is pretty much the conversation stopper at, cocktail parties. happily looking for Martians. But then about 20 years ago or so, our center director at the time had become aware of synthetic biology and thought that this would really be a great enabling technology for humans off planet. And somehow I ended up in the crosshairs, and he now tells the reverse story. This is true. He told me to start a program in synthetic biology for the agency and start commuting to Washington. So I did all those things and discovered that there was a little bit of an inner engineering in me, and realized that there really is a totally different worldview between scientists who look at the world around them and marvel at the beauty. This is, as I'm sure everyone in the room knows, Darwin's birthday was on Wednesday, 216th was week in Iraq, and it's just magnificent what nature has wrought. But when you switch over in the mindset of an engineer, you think, what can I do new today? And most people, certainly not people at NASA, think in terms of life itself as a technology. And I always joke, I work for an agency where people want to see an on-off switch, and my cell phone, which I'm temporarily parting from in the back room, has an on-off switch. And it's rated for what? 2 years? 3 years before you decide to get a new one. I have an arm here that does not have an on-off switch, and it's for about 100 years. So which is the better technology? And so once you start realizing that life itself can become the technology, you're gone with it. And so as part of this whole exploration of what we can do with life as technology to enable human exploration as well as answering scientific questions, and my lab, we have a couple of great people in my lab here right now, trying to get interested in how we could do for aeronautics, we started to get into biomaterials. And so I think I'll probably leave it there because I'll be talking much more extensively about it later. But we sharing multiple things from polymers, mycelia, we'll work with cellulose, and again, life itself down to the molecular level is a biomaterial. And so that I don't forget, I did want to call out Dr. Justin Snyder, who's in the room, who is the one who said, oh, it's great bioprinting and basically anything engineering in the lab. And it's just been amazing having her with us in the lab. And Dr. Rolando Cruz Perez, who is somewhere in the room. He's the one who rescued me at the door earlier today. Oh, there he is. And he's our top fungal synthetic biologist. The architecture, biomining, and probably 10 other things that he probably keeps secret from me. But thank you so much for being here and supporting this. And of course, my dear friend Martin is associated with the project. So I think we'll just take it from there. Oh, and my long-suffering cousin. So to Mark me before I embarrass
And there's the right slide. It really wasn't. I was somewhat by time. There's anything that I get. We'll go over it. So, yes, I'm Martin Dave Robertson. So I'm a professor of emerging technologies at Convergence University in the UK. So we've traveled quite a long way to be here today. I just need to say to the organisers that every mile of the worth it, for sure. This has been such an amazing event called When Together. It has some time to go yet. I won't tramp a little too much of it, frankly. So I used to want to say unique background, but in this context, there's So I was trained as an architect. I then moved into the world of computation as it relates to architecture in different ways, and turned wonders of synthetic biology. Through a very long cultural process, I ended up taking a sabbatical master's in synthetic biology, and then founded initially a research centre called the Look at Biotechnology in the Built Environment, the HBBE, and a large group within that which I now co-lead. I firmly did with my wife, John, who's a molecular microbiologist. So I was just reflecting on this actually. We were talking before about finding unicorns. So for those of you who weren't in the morning session, unicorn is the ideal collaborator in the alternatives field. So if you're a designer and you find a scientist who's willing to work with you, you hold on to them. And my recommendation was that. I can't say it will work out for everybody. but it worked out for me. I now have children. It's kind of started. So we work together. We run. In fact, now I've moved institutions recently, so we have the same land together. So we moved all our resources into one place. It's extraordinary opportunity and amazing to be able to do. We have work actually in the exhibition. So in breaks, I really encourage people. Maybe I'll head out there as well. I'd love to show those who haven't seen it some of the bits and pieces. I'm not going to talk about that because I wanted to reflect a little bit from this morning's presentation as well and pick up some of that. I decided to talk this image on the left, which has kind of got a little bit garbled in translation, but is not something I usually show in presentation. This is actually part of an internal document that we have. It's our internal route strategy document. But we start off with the research question in our group, and our group's about 20 people at this point. We have molecular microbiologists, we have material scientists, designers, and then we collaborate with lots of different people, chemists and so on, to do what we do. The central question that we ask every week when we have our group meetings: can we grow buildings? Until starting group, and yes, we do want to be able to grow a building, to have something that starts as something like a seed and self-assembles into something that we would recognize as an architectural structure, but that also will survive, learn, be able to adapt and change things in mind. That's a simple question, but the answers to that are very complex on many different levels. So we have to break that down into different parts. And so the way we think about it, and we're well funded, we have to think in terms of technology readiness level, that NASA has given us this measuring stick for the way that we think about technology. If we go from the right here, we think about the very early TRL work, which is where we get a lot of our research funding from. So I pretend most of the time not to be an architect, but I do more biological engineering, and we get our research from very early technology readiness level things that are where we measure success in millimeters, so we don't have things that are structurally there. So the first 4 or 5 years while I was going and doing the rounds and I used to work like you were, most of my images to architectural audience were electron microscope things. It was not super satisfying. And I'm thinking, what is the architectural imminence of these things? And you'll say, oh, just give me some on this. We'll get but we get a lot of our funding through that, and that means that we can build a stadium group. So we have the equivalent of NSA, and we've got credibility now within our equivalent of NSA. We can get, not with complete success, but with relative success enough to really run a stable research group that have and do the very expensive work of biology, and it is a very expensive field. So we've been thinking about that. So that's the ideal, and so we have the first project that we ever did in this field was in thinking soils. And the pitch was, can we make a self-recycling building foundations, micro to the soil, technical changes, and we model soil response? That was my question. That's in my master's degree. And that then led on to a number of projects looking for pressure sensing, mechanical sensing bacteria, looking at microorganisms, calcite precipitation as a way of cementing science and so on. It led to a lot of projects all around the same thing, but that moved us in different ways. We are still now 10 years into that project. We've had a number of publications, but I'm always promising the major publication will be this year. I'm pretty sure it's going to be this year. It's sitting in my inbox. If I have a lot of them flying on the way back, I'm like, finish it. We'll submit that. But then as we've worked, we've sort of broken that question down into other parts which go up a little bit in terms of technology readiness. So a key area for us is called Convergence. Was introduced beautifully by Jenny yesterday, the process by which self-assemble to make form and the structure and shape. This has been predominantly worked on by my PhD students, and it is the theme of the projects, the number of the projects you see upstairs. Actually, microbes, which are not generally thought of as having a natural genesis in a way that cellular organisms are, but there are pattern formations, the way in which matter is organized in space and over time, which is very interesting. And as designers who are interested in space, materials, assembly, geometries, we're really interested in what those processes are and whether we can harness and actually enter into a dialogue with those processes so we can derive forms that we're interested in, but also new and exciting forms as well. And some of the work you can see, particularly this exhibition, is really covering that aspect of it. And then as we've gone up through the technology readiness, we've sort of begun to realize that there are certain materials that people work with and are scalable naturally. So when we set up the lab, I said, the one thing that I didn't want to do was anything to do with my silly. And then I had it. And that was with Monica, who's a PhD student who came from Mental Lab, who started working on legislation. One of the first. We had then Dylan as well, started seeing really bringing work in. I'd say half of the labs worked on this reforms. It's a very, fungus is a very plastic organism, so it is liable to all kinds of influences from its environment, and it makes scalable material look really clear. It's a good entry point as well for people who come from outside biology, because you can learn how to break that principle will allow you to create really solid materials like great connection do. I started to do work with, I've even been in primary and secondary schools doing like one on selenium with the next generation of bioengineers that are coming up, and it proves to be a really inspiring thing for them to do. And what we're doing there is we're accepting in some ways this is kind of biomechanical physical digital. I won't go into exactly what that means, but it means offsetting some of the information in a way that we're fabricating into digital systems rather than seeing them as being the biology. So I'm moving away from the idea that there's a magical genetic code that we can just program and that also produce a building. What we're doing is we're deriving biological systems that have very complex interactions with themselves, with their environment, that we're learning a language for, we're trying to alter in order to create materials and structures which are beneficial to us, but also beneficial to their environments as well. And that dialogue is becoming courses and is becoming a way in which we can also promote and indicate our work to others. And then there's the final kind of, on the left is the final kind of pillar, which is the very new mining technology of openness, so we're just nearly there now. And something I think has become, I'm even saying anxiety with our group is the fact that we're in a climate emergency here. So when I go and give a presentation on a technology that might be ready in 60 or 70 years, that some of these things are that far away, the question comes, well, what's the use of that if you don't have a habitable finance of that? And so we have incredible vibrancy within our group, all kinds of different elements that are working together towards these common goals. But we started to realize that some of the elements themselves may be valuable in a much more future context. So I've been talking to various people today, and as I say, if you want to talk afterwards on some of these things, about the fact that we've been working with microbial cellulose, for example, which is a really interesting material in its own right, but through the ways in which we need to treat it, we found things that might, for example, some really good treatments for fire retardants and water materials called worming, but that we can program in really interesting ways. We started realizing this is actually quite high technology readiness. We can apply it to these materials straight away, and we can do tests on them. We can actually solve some real problems around adhesives and other things with some of the parts of these other projects which have these broader goals, the things that we might be able to introduce now. And so we're just beginning to start to work with companies and even consider spinning out our technologies ourselves in order to get these things into market quickly. So that's the kind of spectrum, and that's in a way kind of behind in the pitch of the group, the way that we're trying to organize our research. And so I thought I'd leave that there as maybe a provocation as much as anything for a conversation that we'll have today. Cut.
All right, well, I couldn't say I'm not a scientist. You got that, you picked that up. So I'm an architect. I spent about a decade and a half in practice designing buildings for scientists, actually. Did laboratory buildings for teaching and research on college and university campuses. I loved working with scientists, complexity and the challenges that were involved in that. And so I do have a thing that is going on in this room. I made a career. I had an opportunity to pivot into technology, joining the software startup, Revit Technology Corporation, and helped them launch their building product, which was then acquired by Autodesk in 2002. And my role around that time for the next few years was popularizing and evangelizing the idea of building information modeling into the market. Actually wrote the white paper accredited to Autodesk generally that introduced that term and was picked up by the analyst community. And so it was a great example of bringing a new idea into the market, something that in marketing that we called category creation, created a new category that people would change the understanding that people have technology. I think there's some of them applicability for some of those ideas to what we're going to be talking about here. I then moved into creating new products that were built, to extend the capabilities of BIM, largely through hiring small companies, startups that had sort of theses of the solution, putting those together and launching new products. So I brought a number of new products to market, whole go-to-market process, which I think is also going to be relevant to some of the things that we're talking about here today. And then having been so involved with startups, I became interested in innovation and entrepreneurship, and over the last 10 years, Autodesk, I've had a couple of roles fostering innovation, engaging with startups, doing kind of internal startup activities. I built out our the Innovation Center, Autodesk Innovation Center in Boston, which being opened in 2016. Some of you within that facility. It won an award for fostering innovation in the AEC industry from the American Society of Civil Engineers a year after it opened. And probably more important than that facility, along with it, we created a network of researchers, startups, researchers from industry and academia, and startups who could use that facility. Since we did the build, we really couldn't staff it ourselves fully. So we just invited everybody else to come in and use it. That turned into a massive program. Over 4 years, we've had over 600 different teams who came into that facility, as well as 2 others that I that take on management of it. Toronto and San Francisco, so when you go Pier 9, here became one of those facilities, not called technology centers. We had thousands of people those 4 years who were actually advantaged, come in, use the space, who did their work there. It's very energetic programs. I love it, and it led to my interest in collaborative innovation as a way of moving ideas into kind of reality, into the market. I left Autodesk in August, specifically to focus on fostering, mentoring, coaching researchers and early stage startups who were trying to bring innovation into the building industry. So I remain passionate about the building industry. I remain passionate about innovation. I'm very excited to be on this panel talking about exactly that.
Excellent. Thank you so much. I'm going to hear a bit more from the class. As we get into our discussion here, each of you shared with us some of the broader imperatives here propelling your work forward, and some of the why biomaterials. I think you kind of already answered that to a certain extent. So I guess what I would love it if you could elaborate upon is, with that imperative in mind, why you are invested in not only biomaterials research, but seeing it implemented, proliferate, application, right? That these are all related terms, but perhaps distinct in some ways. As we imagine kind of each of you implementing this work, what does scaling look like in that context? Is it merely a kind of matter of kind of taking the work that you're doing, the scale of the lab or the studio, and kind of amplifying that and distributing it more widely? Or are there other ways in which scaling might almost be more organizational principle of proceeding from sort of primitive, let's say, kind of offerings to someone that's perhaps a little bit more sophisticated over time? So it'd be wonderful to hear your thoughts. Glenn, do you maybe want to start?
Okay, so
You go on. Yeah, why don't you?
sorry, I can. But so how do I think about scaling it, like making, I guess, beyond what my lab is doing and so on? I think the main thing is if there is a need, right? So if let's say there is a specific need, like for example, when we start working with this biodegradable polymer, obviously there is a lot of need in it, in like a scaffold, tissue scaffold. That's when we can thrive in that. So now going back to what I interested. So for example, this curve business, like curving. Personally, I find it intriguing. That's what I would like to explore. Now the question is, how can I sell it, right? Who would be interested in it? It's a bit challenging, like as an from academic point of view, because our scope is very limited. If you realize how academics actually work, we are very traditional. Going back to like our undergraduate subject, right? We have curriculum that we have to teach the students. If you look at it, it's very traditional, basic. It's hardly that we introduce all of these new ideas. It might take a while, until, okay, yes, this being used, now we have to teach the student because they need it. It's not the other way around, the academic, now there is new idea, let's introduce it to the student. I'm talking about undergrad student. It's not like that. So they are not being exposed to all of these new ideas, mostly on the research front. But then in the university-wise, I feel, this is my personal experience, we are more like focused in our need, right? Get used to what we know, it's hardly that we reach out to other entity or other department or other collaborators, so we are not aware what we can do with it. So the same thing, I said, if this has to be scalable, there should be a market, a need. Whether there is an urgent need, now we talk about like fire in LA area, right? Maybe urgent need to think about new material, not made of wood for residential. That's probably how you can scale it. Otherwise, it will be slow. That's what I think. It's just going back to the idea of polymer. I do a lot of work on polymer, right? Now polymer seems to be an enemy of everyone. It's pollution and so on. But before, polymer is the champion of everything, right? So in 50s, we think about polymer, we can make building out of polymer and so on. How polymer booming is because of the war, Second World War, right? They want to have fast material, durable. We want to have material that lasts longer, lasts forever. Now we don't want it to last forever, which is interesting. But at that time, because there is a need for like army, like rope, parachute, and so on, that's what nylon is booming. But then the polymers actually exist before the Second World War. It's already in 1800. They do exist, but it's not that being used widely. So that maybe if there is a disruptive event, that's where things can be true. That's all. What I think.
What is the workings? That goes.
So, in spite of what Elon may think, as a civil servant, I've taken a vow of poverty. When I hear scale up, I'm thinking more of going from our lab prototypes of sort of building on Mars to something that's habitable. We don't do scale up as terms of industrial scale up and worried about quarterly profits and so on because we're a nonprofit agency. So where I think one concern is again from scaling up from lab models and lab experiments. So right now Rolanda is doing a lot of work on comparing biomaterials that are grown in little tiny ice cube trays. And obviously that's a long way from building a 2,000 square foot house on Mars. And so that's where we are in terms of scale up, but it doesn't worry me at all because something like a fungus scales very easily. Or we've been involved in using a fungal platform for biomining. So I was all day yesterday after giving a talk on mining. Can you scale? And absolutely, fungi will just keep growing till they run out of food. They don't care, and you don't need to build a big factory to do it. So I think that actually biomaterials are something that scales really nicely. But again, I'm not in the business of, changing this planet. I'm worrying about changing another planet right now. Thank you. Stay.
See, an interesting question about resource utilization. What's the answer term for this? It's in situ resource utilizations.
Exactly.
There's a thing which I find quite influential.
Always been
In situ resource utilization. So there are many questions, there are many dimensions of the scalability thing. We could have an entire conference just on enough. But we do get approached quite a lot by biomaterials companies now who wants us to do some testing or also do some biological characterization for them. And we've seen a lot of them hit the scalability limits. They'll do something really good in the lab and then they can't scale it. There's lots of problems with that. There's some just biophysical problems that fix things at a larger scale and then works dimension. But often it's resource utilization. So there's this, you can produce something a lot from the chemicals that you're buying from whatever surrounding does, and then you sell them all as maybe hundreds of kilograms of basic chemicals. And biology is often complexity in and complexity out as well. So you don't just, very few biological processes that solve an absolute thing. There are certain lessons that can do it. Then you find you're in food chain where one relies on another and so on. And so a lot of the scalability issues are not understanding that complexity. And just to give you a very simple example of this, we spoke to a company that made a hemp-based building installation, and they were doing incredibly good work. Their expansion was always the vertical on the chart. Some of the development of their facility, they were building more factory, they had the investment to do it. And they started when hemp was a waste resource that they could utilize, and now it is a reviewed valuable commodity. And they were about to, the UK supply of hemp was about to hit, so their growth would just stop, and they would not continue to grow anymore until they started buying farms and growing hemp. And of course, then they competed with food, and actually this is the space exploration problem, but if we have a little bit more of resources that we can use, but it's the same issue. And I think that a lot of the biomaterials projects are very narrowly focused on the modes which will produce something cool and interesting in the lab and present it, without thinking about any kind of food chain that requires you to make anything with people to be biomaterial, and that seems to be a fundamental issue.
Something lost. I think actually you brought up sure, I'll take that. A really interesting point when you talk about buying chemicals and so on. I mean, we treat these organisms like they're rarefied butterflies, if I can mix metaphors. And so we get them, they are ultra pure nutrients, this and that. And the fact is, in the real world, yeast live on rotting street. They don't live on a defined medium, for it. And so, I think that's also been a problem that the mindset of the average biologist is go to the Sigma catalog first rather than seeing what organisms actually eat in nature.
Yeah. I'm actually really taken with your hemp story, because that's one thing that's been on my mind is, biomaterials are very good at that, the exhibit it. Beautiful stuff. And, but just scaling means industrialization. And, this has become less charismatic as you do that. But what I like to do is, I like to talk about scaling and bringing in, what you called yesterday, we were talking an invention and then an innovation to the world in a way that it makes real impact, changes the world in some meaningful way. And in one of my worlds, that would be called go-to-market. We bring the product to market. And the product could be a material, it could be a software, and so was in my case, it could be banana. And none of those things are particularly valued. They don't have any particular value until you surround them with everything that is needed to make the user or the customer or the person who's making use of it successful in using it in the way that it was intended. And that's called the whole product, included in any kind of marketing terms. And that means, not only a piece of software, but all of the training, a channel that'll gets it into the customer's hands, ways that the customer can, implement it on a computer. I mentioned support already, documentation, let that anybody ever wanted to do that. So all of those things, and then you have to also explain it in a way that the market can understand it so that they know, why should I even be interested in this? All of that is part of that. A banana, you need transportation infrastructure and logistics, you need some kind of, something that tells people what to do with a banana, right? Take that banana into banana bread, on the kitchen counter from wherever it is grown in South America. And the same thing's going to be needed for bringing materials to a level, an individual material or assembly materials. And one material can have multiple uses you go to markets. An example from literature is bentonite. Bentonite is used in basically scrape it out of the ground, and it's a volcanic clay that's in the presence of water. It's used for below-grade waterproofing in architects. Many of you may know that. It's also used for lining wells. for drilling or oil and water. It's used in kitty litter. If you have a bag of kitty litter and you got a bag full of bentonite, it's used in mud mats for your babies, and it's used in cosmetics. And nobody who uses it in one of those spaces cares about any of those. So it says they're making 5 different products, even pretty much the same material. So it's it's a fascinating high lift project to bring something to market in that way. And we're talking about collaboration on the first going to market with something, scaling it in the sense that I'm talking about is collaboration on steroids. You are, I think people who eventually bring an innovation to market often feel that they've lost touch with innovation in some way, right? It's they lit the fuse on something and then it's taking on. And I think that embracing that process from science to market is part of scaling. I will add that many institutions now recently, Cornell Tech in Roosevelt Island, the Silk Lab that was mentioned earlier, have an interest in starting incubators specifically for this process, for bringing innovations that are coming out of their labs that have been operating for a few years and are starting to bear fruit. Now what do we do with it next? So we can take it to market through, sort of the venture investment process. So that's very encouraging. I think it's a very exciting world for researchers to engage in.
Tim, thank you for that. Fascinating. I mean, it sounds as if many of these responses to prairie degrees are really come down to being about production. And I guess I'm curious to hear a little bit about how you see your own role with respect to production. Is the role of the researcher, the innovator, and the role of the producer, are those two different bodies? And Rick, you mentioned kind of collaboration, right? To what extent is that actually really more about setting up a kind of collaborative process with a partner? And if that's the case, I guess I would love to hear a little bit about what you think that ideal partner looks like for biomaterials. I mean, some obvious candidates that might come to mind are biotechnology or agriculture or food production, but if you were to design your ideal collaborator, your ideal producing partner, what would be critical to this sort of larger biomaterials project?
I can start to what you like. So I think there are partners that sort of sound like they make sense, like Cryotech, I think a technology firm that you scale all of the reactors and things that you need for producing stuff. I think agribusiness is a good place maybe to look for partners if you're dealing with an agricultural product, that's growing things. I pick companies that make food. They have a lot of process knowledge that could help you scale an innovation in biotechnology. So there are the sort of process partners that I think that you could be beneficial. There's also partners, though, strategic partners that would be called into sort of the investment community. And those are companies that either can help you get the product to market after you've begun to scale it. So they're a channel, either they may have stores all over the world, or something, some way if they have a dealership or something that allows you to get a material or a product out into the market, or they may be a company that could actually use it. So in case of many of the examples that biomaterials that we're talking about, a production home builder, for example, that builds wall-to-wall Douglas cornfields with new housing products like Lennar Construction would be an example of this. They've just built thousands and thousands of houses in the US. And so if you had something that ultimately would be more effective and cheaper for them, they could actually be a whole market for that product in itself, and so we'll prove it out. So those could be the kind of partners that I would look for.
So you alluded to the sort of model we have is one. We split our projects into 3 types. So we have our invention projects, which are the latest or the generally felons, so where they're not well known yet. the innovation projects, which are the incremental developments that get me to something, and the big impact projects, which are those things that are close to my close to having impact of one sort or another. And so, and they do involve a different mindset. So I think as academics, we're often very taken with the invention projects, because those are the really cool ones that get with really high-cited papers, where, you know, you get a lot of kudos for that. And as designers, we like the new things, and they're really cool things that we show. We have, you know, be there. Innovations is you need focus, and it's not often not very glamorous. Because people will say, "Oh, I've seen that before," but they haven't seen that before. I say it's really interesting. It was if where I live, I live very close to where Stevenson built a rocket, which is generally in the historical test, but it's kind of the first steam engine. It was actually the first commercial steam engine. So before it, there'd been the invention of all the things that led to the steam engine, but it was the first one where it was slightly cheaper to run than a horse for all the coal. That was the moment it became a commercially viable thing, and then we had the Industrial Revolution, from the steam-driven industrial, and that. What got them there is thousands and thousands of mind innovations and cartoon and techniques and so on. And that's just hard work, and it is not that well rewarded. And that innovation gap is often a problem with technology. And then you've got the impact stuff, and you need a laser-like focus and a complete understanding of where you're going, what we're doing. And so, and the problem for us as academics when we're looking for those partners is that we're quite good at the invention, or we like the invention stage, and there are actually not a lot of benefits to us to going through the really hard innovation steps that it takes to get us there. So it's finding those sorts of partners, and of course the funding that comes with it to do that kind of like work.
There we go.
So as usual, I'm the odd man out here. So what, you know, our conceit is to try to get something that takes as little human intervention as possible to work off planet, whether it's Venus or Mars. And, you know, unlike here where a construction worker might be not the major cost, or, you know, it's less specialized thing, astronaut time is really valuable. So we need to focus not on autonomous construction methods, self-inflating, self-building homes, but we also are dealing with locations that don't have a petrochemical industry. They don't have a current solution. We've had humans on the moon, but they've leaked in their rocket ships. So there really wasn't the solution that we need for long-term human survival. And so I actually really feel that although we have all these challenges, because we don't have an existing infrastructure, we're able to really focus on that idea in innovation stage without worrying currently about scale up or the investors or anything, as long as we can get, you know, the space investors to invest in it. Because again, we don't need to compete with an existing technology. And so I really firmly believe that we're going to be able to help make those jumps that then people back to Earth will be able to take advantage of. Yeah.
Okay, so I just want to add what had been said before. I do agree, like you need to find like a right collaborator at different steps, right? Whether it's innovation, invention, and so on. But particularly, I found in like a civil structure, I think dealing with regulation is also has been really difficult, because you need a code, like building code. Like who approved that? Who come up with that code? I guess to some extent, like article translation, right? So I don't know where the change is, but they have to be on board. Otherwise, okay, you have this cool material, you show them, okay, it's fire resistant, everything, but if it is not in the code, nobody gonna use it. Nobody gonna build from it, right? So I guess that's another dimension. If you want to push through this biomaterial, they have to be aware. They have to be convinced. Yes, it will work, because I can understand why they are being conservative. Because if the building collapses, you know, you can see, right, how much catastrophic it's gonna be than just, okay, a car malfunction. There's a different mindset. That's right.
Well, our time is running short, so sadly we only have time for one more question, but maybe as a way to sort of round out this conversation, to build on what you were just saying, you know, in light particularly of kind of what happened yesterday, the swearing in of a health secretary who doesn't believe in vaccinations, and prevailing sentiment worldwide, which is becoming increasingly anti-science every day. I guess I'm curious what you see as the hurdles, the obstacles to, in a way, getting a more of a widespread public buy-in for biomaterials, given that we probably have a room full of early adopters here. This is the already converted. Perhaps, a portion of that is the success rate of biomaterials have reached so far. So how do we get over that next hump in terms of converting people? What are some of the hurdles that you see in terms of popular sentiment and the wider proliferation of the biomaterials mandate the message?
Right, so the issue is they rely on the politics, they always cycle up and down, like who is now ruling the country, right? But I do think maybe this day everybody using social media, right? Sometimes information spread very fast with social media. So we can make media help us like advertising. Okay, hey, we have all this material, cool material, and there is a promise to do that. Now, for example, with the idea of this biomaterial, fungi, mycelium, engineered living material, I think it's very recent that we heard about it. Even people in academia, if I asked my colleague, do you know engineered living material? What is that? They don't know, unless you are working in the field, right? So we are talking about people in academia who's working with materials. They never heard about it. So I think one way to spread this, like social media, is because take advantage of it. If the young generation are aware of it, because they are ultimately the one who's gonna take over. Like, if they buy it, they're gonna push through. That's what I.
Sure.
After we go green. Actually, I think it's easier than that because it's a continuum. I mean, you look around you real, many of us are wearing biomaterials. We've got leather on, we've got wool, we've got cotton, we've got silk. Surely there's wood in this room somewhere. Many houses are built out of wood. All of these are biomaterials. Humans used to build structures out of bone. There's evidence Neanderthals out. I mean, we have used biomaterials for building and for clothing throughout human history. And so I think maybe some of the problem is introducing a new academic term. And it's not actually the concept of using biomaterials, it's the terminology. And I should add, being in a biomed school at Brown University, a lot of people in academia consider biomaterials strictly medically related materials. And that's also an issue, too. So I think that some of it really is not a matter of, awareness or problems or anything else. It's simply setting up new terminology that then makes it sound like it's something radically different. And then I think the second thing is having companies, and I'm supposed to mention companies where you would ask, but companies like Michael Works, for example, making the high-end handbags out of fungal materials and then getting the media attention for it, I think also makes it attractive. And, I do think actually having, say, organizations like NASA put their meatball logo on it, helps also with acceptance. But again, I think the bottom line is we've been using biomaterials throughout human history. It's nothing new at all. It's only something new ones.
The fashion and textile example is quite useful here, because I think that the fashion design and textile design in particular have gone ahead of the game in some ways. It is certainly more so than architecture, maybe because they're more scalable products. But there's a sort of two approaches to it, which is rather interesting. One is actually a lot of these emerging and new biomaterials, so things like mycelium leather, microcellulose leathers and so on. The fact that I'm using the term leather there is a sign that we're in the horseless carriage phase of these materials. So in a way, they're being sold to the public as a direct one-for-one replacement, and they're being evaluated on the basis of the properties that people of the material has. And that actually leads to some problems, because you end up with treatments of some of these materials that actually make a lot less healthy and so on than you might realize. The other option, and I think speaking now as a designer, so pretending that I'm design and pretending to be a fire engineer, is that there are so many emergent, interesting properties of the materials, and as designers, we can sell loads of aspects of it. So we're really interested in things like emergent patterns, for example, on a material, actually showing off biological processes and making them part of the aesthetic of the objects that we're creating, and indeed some of the incredible functions of these materials as well that are getting hidden at the moment by that. And as designers, we can actually make these things incredibly desirable, and that's what I think part of our group would like to be doing as well is moving beyond, as I say, the horseless carriage phase. Accessibility comes through maybe novelty, actually. Maybe it becomes, these things are better than having a resilient bag is better than having a leather bag. So I mean, that's with dimensions. So, well, for example, we just made the publishing get self-healing these materials even when and more. So this is, I think, for me, the answer to that. Certainly, this is, I think, an important designer's role within this context.
Lynn, your comment about, we're surrounded by biomaterials is an interesting one. I have one biomaterial that I was thinking about for this presentation. It's a blended cellulose insulation. It's been around for probably 50 years, right? It's very common in the market. There is a distinction, though, in that a lot of the things that we're talking about transform biology into an unrecognizable form, or into a form that is associated with another material. Like the mycelium leather thing. Oh, isn't that cool? We could make it look like leather. And you can argue, that can help forward an adoption at a luxury or a certain fashion level scale, but in the building industry, that might not be so, I don't know how that works. So they more like torture process, even just so good. I think from a regulatory point of view, there's often, I think, a sense that, today's solutions become tomorrow's problems. Meat plastics, asbestos, Luke's early sugar cane, there's less panels than Hawaii were impregnated with arsenic, so the bugs wouldn't eat them, and just how they were a problem. That kind of stuff. And so people are kind of wondering, okay, well, how do we, not let that happen? It makes us maybe more conservative as a society than we necessarily need to be, in that, yeah, it can be a problem down the road, but it's, maybe it's solving a problem now or can come back for a while. I do think one of the obstacles to how getting these things into market is how are the incentives and rewards for the researcher. You and I commented on this last night. Like another conversation referred to as papers and prizes. That's how we're measured as researchers. We call those papers, we get citations. We move forward in our tenure process. We gain some respect of our community. We get appointed to the become a fellow of whatever professional association or institute, things like that. And the hard work that you're describing, and we're talking about, it doesn't build that kind of career. So either we need to change the perception, self-identity, kind of how our careers are rewarded, or we need to recognize that there's a more complete form of being a researcher that's not just continue with producing those ideas. And I think we have that in our professional associations as well. I was on a panel, as I sometimes have, on alternative careers for architects a few weeks ago, but I realized there's more architects in so-called alternative careers than there are conventional careers. But you wouldn't know it because they're kind of invisible. They're not on the cover of Architecture magazine, and they don't get. And there's a few sort of consolation prizes that they will give you for doing this kind of work. But for the most part, unless you're doing glorious building designs, you're unrecognized sort of Russian. So I think we need to think about our professional identities as designers and practitioners as well.
That's great. Thank you. Well, I fear we've barely only scratched the surface, but we can take some time for some questions. Great. Thank you. I'm going to need to distribute the microphone. I will be the MC. Yeah.
For worship grant. Thank you.
Thank you. So I have a question, or just your thoughts on, it's related to scale and maybe partnerships. So part of the problem with scale is that companies today need to meet unit economics, and that's like investors, the market needs to meet global markets. So, and oftentimes to win, you need to like dominate the market. And because of that, then you like might need hundreds of kilograms of something because you need to make a big old factory. And so I wonder, as one of my advisors used to say, that all atoms are local, and so biology happens locally. And I wonder how, and for you, Rick, what do you think about alternative models of ownership or financing, et cetera, and how that can both solve the problem of scale and then also make the partnerships model?
So it's an interesting point. So you can wait until, a company that's going to acquire a technology, startup, can either wait until it becomes so successful that it's inevitable, by which time it is too expensive for them to acquire. It's done successful, right? Probably not going to get there with a biomaterial. Or they buy it as a startup, as a substitute for doing their own internal research, and often, ends up just sort of becoming part of the branding campaign. It isn't this cool, we're doing this kind of work, but meanwhile we're selling billions of dollars of our real business is over here, and so it never really amounts to anything. So it's a risky, it's kind of a risky balance. Let's see, where would be that? So your question was about pardon?
Like financing, absurd.
One example like cooperatives. So like that long been like black-owned cooperative. There's a big one, right? Jackson Cooperative.
Yeah.
I don't think that we think about that enough. So venture capitalists, investors, want companies to dominate global markets, and maybe that's a problem for biomaterials.
Well, there was I was heading towards that, or towards what happened with ethanol produced from corn. When regulations changed, turned out to be actually relatively environmentally damaging, right? Palm oil as well was another environmentally damaging thing that was, I believe, the sort of result of well-intentioned regulations. That now we have an trend, ethanol scale. People grow kilos of oranges so that they can produce ethanol to go into gasoline in the U.S. and make the U.S. more dependent for a while time. So it's possible through regulatory or policy change to scale. You can get somebody that can do stuff at that level. I don't have alternatives or open source or things like that, but maybe some of you could see models like that.
Rolando, correct me if I'm wrong, but I think what you're getting at is that biomaterials might be ideal for distributed manufacturing.
That's right. Yeah. So we need different business models to fit and that probably helps with a lot of things like workforce, economic resiliency. You can get all kinds of supply chain resilience, etc.
I would just say that I think there's a sort of a biological analogy and a biological reality which is quite useful here. So I have one of the many projects that never got submitted was called manufacturing metabolisms. And so it was based on the idea of, so those cell biology, metabolic networks, the exchanges of massively you get when making proteins, small molecules come into the cell and then the guide itself. This complex, it looks like one of those kind of underground maps and hell kind of pictures. But the reason that is so complex is that the cells are often adapting to whatever their environment is, and some being got some nutrients and switching off genes and on genes to do certain things. And I think within biology, there's therefore an incredible robustness. So you can think about the same biological material with many different routes to it. And so if you extrapolate that out as a manufacturing chain, and you would stick your manufacturing materials, say, next to a farm that's producing water substrate, you would choose a set of metabolic routes to transform that substrate into the material, which is different where you might have a different availability of stuff. So I think there is those kind of mapping exercise that you can do that's quite radically localized production methods using the same fundamental biological building blocks, but just adapted into different inputs and made towards similar outputs. So there is a model there that's kind of interesting. I don't know whether it's being explored significantly as an area of research commitment, but I think it is an interesting one. It's all where we've got biological analogy of the same reality to it.
Yeah, but I think Roland, second point was also that should provide extra resiliency for supply chain disruption. Good, I think so. On shell, all in good control place.
Migor, do we have time for one more question?
I'll just add one quick thing is that sugar beets are processed through a cooperative, it's a multi-state cooperative at a central location, and then that's to get sugar. So biomaterial that could be an interesting model for large scale production of other materials too.
So we have
Thank you for this really interesting conversation, and thank you for your comments on fashion as well, because I'm in the fashion industry. As I've been really nervous all morning with the reference to scale, knowing that despite many decades of working on sustainability in fashion, all the ecological indicators are worse than they were back 30 years ago. And so, and we're very clear that we're producing too much. So this conversation, I was gonna press a little bit more on this scale thing, because I noticed that the language that you were using when you were talking about scaling was very mechanical language, and it was the Horsley color language. And this yesterday and today, you've been talking about pushing against existing codes. And today you talked about letting an aesthetic emerge from the work and not trying to make this new material into the old aesthetic. And so I was hoping that new forms of production, different scales that are not an industrial scale necessarily, or not just feeding into what we already have. And it sounds like that's coming. So I guess I'll get to the question. So the question is there funding for that? And is that where the next innovation is, not so much on the materials, but on how these materials come into being in a radically different way than the one that we know isn't working? Right, because why would we scale into something that we know isn't working, that's depleting too much, generating too much waste? You know what I mean? Certainly in my industry,
If you just take that one briefly, because we're working with a biodesign challenge team. I think there are a few things that we have about BDC teams every year. It's a competition both in New York, and this year we've had a group of fashion students actually. So we've been giving them all the biological skill on microbial cellulose. But they've chosen to take it in a very different direction. So their projects are not to give various competing teams, but with you sound like you're from the UK, so you'll know that. Is it haberdashers a thing in the US? Haberdashery is the notions. Is that the notions in the US? So there's essentially these stores where you would go, and usually the kind of an expert person behind there as well, who is able to advise you on buying wool and buttons and all the things to make your own clothing. And they've decided that the most interesting thing about microbial cellulose is the fact that it's somewhat like a brewery process. It's something that you can learn yourself. And they've worked out many different ways of making it into different things. And also because it's quite biodegradable, it can be something which is an ongoing process. So it gives you an ongoing, if you're developing your own garment, you will have an ongoing process where you're developing, you're growing parts of it, you're exchanging parts of it, you're fixing parts of it. It's something which will evolve with you, and this is their central concept. And actually the economic model is the haberdashery, or the notion, which is to say that you will be there, there's somebody who will have bioreactors and then new types of bacteria that will help you make these things. So they have a completely different view. Mine has been more, I guess, constrained by the thinking of this as a scalable industrial model. And actually in conversation with them, they've rather pushed back on that idea and gone for completely different routes of what we do in the same way. So I think there is openness, whether there are openness funding this area is find something else. And so we are juggling when we're getting funding, it's very much following the kind of industrial economic strategies that our governments have, which are that to do the same but with bioinfluence of it rather than this. I think it's a completely legitimate question to say, is that the right motto?
I just a couple of maybe relevant observations. One is that in some cultures, I think in some parts of the Czech Republic, for example, there's a tradition of families making their own brandy from the fruit of the trees that are going to be in the ground. And so they harvest these and they, do the brandy thing. And they have distilleries in the neighborhood. Like somewhere there will be a small distillery that will, boot up. I guess it's kind of like bootlegging in the U.S. at one time. But so there is a model for, some biological end product being made like that. On sort of the opposite end of the spectrum, one of the things, one of the conversations over the mass timber is the industrialization forest, right? Industrial pine that they could use for making wood products, not just mass timbering. And I came across a company called Hereditable. You can really inherit something from Hereditable.ag, agriculture. They're a spin out from Google X. They're being advised by a prominent researcher from the University of Minnesota, and they are applying data principles to the breeding and hybridization of plants. They're targeting primarily food chains. This is the kind of basically process that made wheat more productive and increased the ability to feed the world. They're applying it by using data and algorithms and other things I don't entirely understand. They're making this far more expedient, more predictable processes. They also are working to make other species of trees suitable in the way that industrial pine is suitable for some of the building industry applications with a specific goal of increasing the diversity of the forests where this raw material, this feedstock is grown, which I thought was pretty encouraging and also can be very relevant to biomaterial research.
Well, I think that's probably all the time we have for this session, sadly. Just the tip of the mycological iceberg, perhaps. But thank you so much to all of our panelists. Really appreciate your insights and CCA.
So we'll gather back at 3 o'clock. But we encourage everyone to go up to the exhibition now. You go out the door, go to the next building, there's an elevator or a stair, and it's on the second floor, then a back gallery to the left. And some of us are going to go up there, so you can ask us questions when you're there.
So what now, sir?